All right, we are back and ready to get some more geometry knowledge. So let's look at postulates and proofs. Now I'm going to kind of combine this a little bit with another section because in this section they want you to do informal proofs. I believe in more formal proofs because I think that's a little bit easier to understand. Anyway, you're going to identify and use basic postulates about points, lines, and planes, and you're going to use that to help you with proofs. You're also going to use some algebraic ideas to help you with that. Now, some things like definitions of certain things you should already know. So we're going to have to kind of like differentiate when we start using some of those ideas. So first off, what is a postulate? A postulate is, or an axiom, is a statement that is accepted as true without proof. It is not a definition, but is basically kind of like a statement that we say we have to accept as true because, well, there's just no really great way to prove it. For example, saying a line contains at least 2 points, that's like kind of like in there. Anyways, on page 127, you will see the next few postulates. So if you want to copy those down off the thing because you can't see them that well off the video, that's fine. You can get them from the book later. So, through any 2 points, there is exactly one line. Through any 3 non-collinear points, there is exactly one plane. A line contains at least 2 points. A plane contains at least 3 non-collinear points. If 2 points lie in a plane, then the entire line containing those points lies in that plane. Okay, 2 lines intersect, then their intersection is exactly 1 point. 2 planes intersect, their intersection is at 1 line. So there's 7 postulates right there, not to mention your definition of a point, a line, a plane, a midpoint, all those definitions that we've already done before. So you got to kind of keep that in mind. More than likely what I will do is give you all the ones that you need to put onto, say, a note page. I think this one's going to be a note page for this test. All right, so we're going to analyze statements using postulates. So first off, we want to determine whether each statement is always, sometimes, or never true. Explain your reasoning. For example, if 2 coplanar lines intersect, then the point of intersection lies on the same plane. Okay, keep in mind, what does it mean to be coplanar? It means they're on the same plane. So this one is always because you have 2 points that are always on the same plane. And using postulate 2.5, going back to here, 2.5, if 2 points lie on a plane, then the entire line containing those points lies on a plane. So if we go back to that, then what that is saying is that if I say here's a plane and I've got 2 lines that are on that plane, then these points that are here and here are also on the plane, but that means the intersection is also on the plane. Okay? So, got to be careful with these because these can be kind of tricky. All right, 4 points are non-collinear. Well, that's sometimes. You could have some points that could be non-collinear, but keep in mind that using postulate 2.3, that says there is at least, going back over here, not that one, that one. A line contains at least 2 points. So what does that mean? That means that a line can have 2 points, it can have 3 points, it could have 4 points. So it is possible 4 points could be non-collinear, but it's also possible that they may not. That they may be on the same line. There we go. That's what I meant to say. All right, let's do one more. 2 intersecting lines determine a plane. Okay, so if 2 lines intersect, they have to determine a plane. This one is always, because if 2 lines intersect, then there's at least 3 non-collinear points, and by having 3 non-collinear points, then we determine a plane, as postulate 2.2 states. So you kind of have to visualize that. Like if I take 2 lines and intersect them, then there's at least 3 points, because like I could have 2 points here and 1 point on this one that are not collinear, so I make a plane. All right, so the next part is a formal proof. Okay, so this is where we start getting to the idea of proofing. Now, proofing, the way a formal proof works is I'm not going to do an informal proof. I'd rather do a formal proof. A formal proof says you have your statements. Notice your first one is always going to be your given. Then you're going to list more statements that help you get to what they want you to get to, wherever, however many steps that may be. I'm not going to put steps here. And then you got your reasoning at there. But every single time you have to give reasons for each statement that you put down. For example, given that m is the midpoint of xy, show that xm, the measurement of xm, is the same, is congruent to the measurement of xy. I'm sorry, my. Now, notice here we're saying congruent versus equal. There is a difference between those two. So, congruency means like they have the same measure as compared to equal being exactly the same. When we say something has congruence, that means we're saying that it has the same measure. That is a definition that can be found in the back of your book in the glossary, or it should be found earlier in the book. Anyways, let's look at this. So notice that I started off with what they gave me. M is the midpoint of xy. That's the given. You always start off with the given. Now, by definition of a midpoint, then I could say xm is equal to my. Notice there is no bar, so there is nothing about measure. And then again, that's just definition of a midpoint. Basically, remember, the midpoint cuts things into two equal sections. Then, I could say the measurement of xm and my have the same measure by definition of, again, a midpoint. Because the midpoint says that xm and my should have the same measure because the m is divided into two equal halves. So that means the measurement of xm is congruent to the measurement of my, which basically just means kind of like definition of equality, like that they're equal. Okay, but again, we're using the definition of congruence because it's based of a measure. Okay, so on page 136, you'll see these properties about equality. These are from algebraic properties that we can use to help us with geometric properties. Now, let's use that idea to help us with another proof. Okay, so here is like an informal statement, and it says if angle FGJ is congruent to angle JGK, blah, 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 and angle JGK is congruent to angle KGH, then x must equal 6. Okay, so keep in mind right here that with this drawing, all of this right here is given. And you are trying to prove this little bit right here, x equals 6. So if we start to organize this, we have our statements, and our reasons. And ultimately, what we're trying to get to is that we're saying here that we're saying that we should get to x equals 6. So we would start off again with our given. Angle FGH is congruent to angle JGK, and I should be saying here the measurement, because we're saying a congruency again. Congruency is supposed to be dealing with, I'm sorry, we'll come to that in a second. Okay, so we've got that, and then we're saying angle JGK is congruent to angle KGH. At the same time, we're saying the measurement of angle FGH is congruent to 6x plus 7, and the measurement of angle KGH, whoops, this one's supposed to be J, sorry, let's try that again, J, hold up, okay, I got all my letters correct now because I was getting a little whoopsie messed up there. Okay, so what can I say here? Let's look. Okay, so based off the given saying that like these are equal to each other and these are equal to each other, are congruent to each other, then that means their measurements are congruent by definition of congruent angles. So in other words, what we're saying is that if we're saying the angles are congruent, then their measurements are congruent, which, I mean, kind of makes sense, but, you know, that way we kind of see that. So then what's the next part of this? So based on this, I can now say that these two are congruent because by definition of transitive property. So the transitive property of equality, which allows me to say if two things are equal to one thing, then they're going to be congruent to the other thing, if that makes sense. So Notice here how we're trying to get rid of the congruent signs. I kind of messed up there, but that's partially because I want to be able to get to the math part of this, and we're trying to get to this algebraic part. So the next part here is saying that if the measurement of angle FGH is equal to, well, measurement of FGH is equal to 6x plus 7. I'll do that right in a second. And the other one is equal to 8x minus 5. And we can do that because of a substitute property of equality. So we can substitute in. I'm almost done here, so don't worry. Sorry about this one's going a little long. Okay, so now I'm going to continue this on another slide. So moving on. Okay, so I'm going to subtract 7 from both sides because, like I always say, I like to do numbers to the left, numbers to the right, variables to the left. So I'm moving this 7 over so that way these cancel out, and I'm using the subtraction property of equality to do that. Now, when that happens, what that would do is that would leave me with 6x equals 8x minus 12. And I'm doing that based off the substitution property of equality. Again, when you do something like that, keep in mind that when you basically carry out the property, it's like substitution property, and that should be pretty easy. A lot of these, again, will take time and practice. That's really what it comes down to, guys. And we're doing a lot more with algebra here to kind of convert this. Now, I need to get this one over here, so the next step would be to say 6x minus 8x, 8x minus 8x minus 12. When I do that, again, I'm using the subtraction property of equality. So I'm just going to put here SPE. I'm being a little lazy here. Okay, and then that would give me negative 2x equals negative 12. And again, that's from that's a number 7, by the way. 8, the substitution property again. So I'm just going to put here substitution. And then now I can say divide. So I'm going to say negative 2x divided by negative 2 equals negative 12 divided by negative 2. And again, that's the division property of equality. That's what allows me to do that. So division property of equality. And then finally, again, I've got, say, x equals 6. And that would be based off the substitution property, and I'm done. And there we go. Anyways, I'm going to go ahead and stop there. I've gone a really long time. I didn't mean to, but I wanted to put in this one extra example. If you have any questions, feel free to ask. We will discuss this more. Thank you so much for your time. Y'all take care.